Bismillahirrahmanirrahim. We continue our discussion in analysis concepts and principles. That was when we were discussing requirements analysis. In previous few lectures, we discussed different concepts related to requirements analysis. We'll carry forward the discussion from there in today's lecture as well. First, we need to recap what main points that we were discussed in previous lecture. So far, we have discussed some important concepts within requirement analysis. In previous lectures, we tried to define what is actually requirements. Requirements are the demands of your customer or the end user, which they want to be embedded in a software solution. Your end user or the customer have a perception of the software which they want for their problem. So in requirement analysis, the software engineer, also known as the analyst, who is responsible to analyze customer requirements, need to understand the problem first, the problem for which the customer is demanding a solution, basically a software solution. So requirement analysis is actually to understand the customer problem, the customer environment in which he or she is currently working and the problem is arising. And then he or she has to refine the requirements of customer. Different possible solutions other than the software solutions are also analyzed. If software solution is expensive to be implemented, so other possible better solutions than software are also analyzed. Then after analyzing customer requirements and understanding the problem, we then proceed the task and divide the software requirement analysis phase in further different phases. So 5 different phases had been discussed previously. In first step, problem understanding, problem recognition is done. In second step or in second sub-step, problem evaluation is done. That means if a software solution is possible for the problem being faced by the customer, the environment of customer is analyzed and then solution is synthesized. Maybe more than one solutions can be possible for the problem faced by the customer. That can be software solution and some other alternative solutions are synthesized if possible. Then a model has been designed after analyzing that the software is the only solution to customer problem that can handle the customer situation more properly, more accurately than other alternatives. Then a model is designed. A model is a graphical depiction of the solution, the software solution which is going to be then implemented in the client's environment. What are the major functions? The interaction between the functions, the interfaces of the software with different internal and external environments are defined in shape of a graph on paper in modeling. After modeling or a model has been designed, software requirement specifications are then written. It is a written document in which the problem, the requirements, and the solution, along with the specifications of the solutions, are written on a document which are then reviewed by both the customer and the developer and signed by both the parties. So these are 5 different sub areas of software requirement analysis phase. A different set of a team may handle every different sub-task of requirement analysis phase. So one team may be responsible to handle the problem recognition step. Another team may be responsible for evaluation synthesis, and then subsequently different teams are designed or defined for 3 other sub-steps. After requirement analysis phase is completed, we need to proceed for the collection or requirements gathering. Now, we have defined what is problem, how evaluations should be done, how solution can be synthesized. These are the major steps, but how this process should be started. The main problem is to collect or to dig out the requirements from the customer, as sometimes customer himself is not sure what actually he wants. So we have a requirements in an elicitation process in which we collect or gather requirements from the customer or the end user. Collecting requirements is the major problem within this phase. So different techniques are then used to collect the requirements from the customer. We can start with simple question, answer, or interview, in which we initiate the process of collecting requirements. This can be some informal interview, some sort of questioning, answering session with the customer and the client. This may not be done or completed in one go. You need to arrange settings with customer in different sessions in order to make the customer feel at ease and provide detailed requirements and give you a proper understanding of the problem he is facing in current situation. Another technique that is proposed is FAST, Facilitated Application Specification technique, in which instead of working one-on-one, a group-oriented meeting, a group-oriented interview is designed in FAST, in which a group of developers interact with a group of customers in order to obtain a better understanding and a better requirements understanding from the customer. This helps customer to have more detailed discussion with the developers about the problem they face, since different people from within the customer environment interact with a group of developers. So different brains work together here to reach to a single solution. When we work in FAST, we then apply quality function deployment technique, in which we prioritize the requirements of customer. What is more valuable to customer is highlighted as the more important requirements, and what is least important for the customer are or can be omitted with the permission of the customer. So in quality function deployment, generally the requirements of customer are categorized in 3 categories. In normal requirements, Those are the requirements which are explicitly told by the customer that should be present in the working software. The second category is the expected requirements. Those are requirements which are generally not told by the customer, but they expect that they should be present in the software, otherwise the software will not be acceptable to them. And the last requirement category is the exciting requirements, in which these are those requirements which are generally provided, or these are those functions, those features generally provided by the developer to make the customer happy. These are generally not demanded. So these are optional requirements which are provided to attract the attention of the customer. The last phase of requirements elicitation is to draw the use cases. Use cases is actually the diagrammatic representation of the functions and the user who will be interacting with those functions being developed for a software. So it is a diagrammatic representation of the overall management or operation of the software that is going to be built. Who are the actors who will interact with the system, and with what function every individual actor will interact. So this is a graphical depiction, graphical analysis of the system that is going to be built. So these were the points that we had already covered in previous lectures. In today's discussion, we are going to discuss the important requirements analysis principles. What are the rules, regulations to perform the requirements analysis task, and how these rules will help the analyst to perform his work more accurately and reach to the problem solution more in time. Requirements analysis needs to be done under defined rules and principles. These principles are designed to help the analyst or software engineer to perform his task more accurately, and the target needs to be to solve the problem of customer. So some rules are defined for the requirements analysis, or how the requirements analysis should be done. The first rule says the information domain of a problem must be represented and understood. Now, what does this mean? All the software applications can be collectively known as data processing. Interestingly, this term contains a key to our understanding of software requirements. Software is built to process data, to transform data from one form to another, that is, to accept the input, manipulate it in some way, and generate the output. So this fundamental statement of objective is true whether we build batch software for some payroll system or real-time embedded software to control the fluid flow or the fuel flow to an automobile engine. It is important to note that software also processes events. An event represents some aspect of system control and is really nothing more than Boolean data, which is in form of either true or false or in on or off state. For example, a pressure sensor detects that pressure exceeds a safe value and sends an alarm signal to monitoring software. That alarm signal is actually an event which controls the behavior of the system. Therefore, the data, which can be either number, text, images, sound, video, or in whatever form, along with the control, which are generally the events, these both reside within the information domain of the problem. So this information domain needs to be properly understood and represented. The first operational analysis principle requires an examination of the information domain and the creation of data model. The information domain contains three different views of data and control, since each is being processed by the computer program. The first view is the information content and its relationship, the relationship among different data items. Second view is the information flow, from where information is getting generated and where it is going. And the third view is the structure of information, the information structure. So in order to have a fully understanding with the information domain, each of these three views need to be considered. The first view is the information content. So information content represents the individual data and control objects that constitute some larger collection of information being transformed by the software. For example, the data object such as paycheck is a composite of a number of important pieces of data. For example, the pay's name, the net amount to be paid, the gross pay, the deductions, and so forth. Therefore, the content of paycheck is defined by the attributes that are needed to create it. Similarly, the content of a control object called system status may be defined by a string of bits. Every bit represents a separate item of information that indicates whether or not a particular device is on or offline. Data and control objects can be related to other data and control objects. For example, the data object paycheck has one or more relationships with the objects time card, employee, bank, and many others. So during the analysis of the information domain, these relationships need to be properly defined. This is similar to the way you draw data flow diagrams, in which you define different objects, data objects, and the flow, along with the relationships between different data and control items. Now the second view was the information flow. Information flow represents the manner in which data and control change as each move through a system. The transformation applied to the data are functions or subfunctions and a program that must perform these functions. So, information flow is actually the diagrammatic representation of what sort of input one function will process and what sort of data it will generate, where that output will move or flow, which data is the input of which function, and the output it generates goes as input to some other function. So this actually represents the movement or flow of information. Data and control that move between two functions actually define the interface between two functions. The third view was the information structure. Information structure represents the internal organization of various data and control items. are data or control items to be organized as an n-dimensional table or as a hierarchical tree structure. So this is the internal representation of data. Either you organize it in shape of table or in shape of tree. For example, in databases, you design or define the data or store the data, or the structure of information is in shape of a table. Within the context of the structure, what information is related to other information? These questions need to be answered for giving structure to your information. Is all information contained within a single structure, or are distinct structures need to be used? For example, you use arrays to store your data or information. You use linked list if array is not proper structure for your information. So you use other alternative form of data structures. So I hope information domain must be clear to you. Now the second aspect of this principle is the modeling. We create functional models to gain a better understanding of the actual entity to be built. When the entity is a physical thing, for example, a building, a plane, or a machine, we can build a model that is identical in form and shape but smaller in scale. Generally, you have seen the models of buildings or bridges, but in small scale. However, when the entity is to be built is a software, then our model must take a different form. It must be capable of representing the information that software transforms, the functions that enable this transformation to occur, and the behavior of the system as the transformation is taking place. So the model is quite different when it comes to software. You need to have three things defined in your model. First, the functions, the data that is going to act on these functions, the changes or the transformation that is going to happen when the functions are going to be applied on that data, and the behavior the system will show in response to such transformations. So the second and third operational analysis principles require that we build models of the function and behavior. So here you can see the second principle says that functions need to be properly defined and the behavior of the software must be represented. So these two principles are related. So when you have a proper model in place, these two principles are going to be fulfilled. Now, what are functional models? Software transforms information, and in order to accomplish this, it must perform at least three common functions such as input, processing, and output, which is generally the definition of your computer. When fundamental or the functional model of an application is created, the software engineer mainly focuses on problem-specific functions. That means the major functions are generally drawn, major functions, not the minor ones. The major function which will ultimately handle the major requirements of the customer. So the functional model begins with a single context level model. So over a series of iterations, more and more functional detail is provided until a thorough diagram or a thorough model of all the system functionality is represented within the model. So in the start, when you design a model, you draw the major functions. So the more analysis goes on, this diagram goes more refined. The functions are then broken down in sub-functions until the final structure or the final number of functions are defined on the paper. Now, what are the behavior models? The third analysis principle, which shows the behavior of the system need to be represented. Most software responds to events from the outside world. This stimulus or response characteristic form the basis of the behavioral model. So generally, your system responds to events, which may be some internal events or maybe external events. That means external to the system, external to the computer, that may be responsible to generate, to show some, to compel your software to show some specific behavior. A computer program always exists in some state, an externally observable mode of behavior. This is known as a state. For example, waiting state, waiting to have your input. Computing state, when it is processing your data. Printing state, when it is printing your data, or any other state. This state is then changed only when some event occurs. If your application is waiting for the input, so input is the event. When you give the input, the behavior of the system will change and it will start processing your input. For example, software will remain in this wait state until an internal clock indicates that some time interval has passed. Number 2, some external event, for example, a mouse movement causes an interrupt. So in that case, your system may be waiting. Or number 3, in some cases, an external system signals the software to act in some manner. So these are different states in which, or different condition in which a system generally moves to the wait state. A behavioral model creates a representation of the states of the software and the events that causes a software to change its state. So you, along with the functions, you must have to define the behavior of the system. When a system is in specific state, what behavior it must be representing when that event goes over. When it is in some state, when a system is in specific state, that means it is waiting for some internal or external event. Internal events are those which are internal to your computer. For example, the clock, the system clock. If your application is waiting for your system's clock, so that is internal event. But if it is waiting for the user to give it some input, that is external event. So the state of the system depends on event, and as soon as the event occurs, the behavior of the system needs to be monitored. So those specific behaviors must be represented as well. The models created during requirements analysis serve a number of important roles. Number 1, the model helps the analyst in understanding the information, function, and behavior of a system, thereby making the requirements analysis task more easier and more systematic. So, the analysis phase helps the software analyst to properly understand the information or the data, the functions that are to be created for the system, and the behavior of the system. The second role is that the model becomes the focal point for review. When you design the model, this is then becomes the point for review for both the parties, the developer and the customer. And therefore, the key to a determination of completeness, consistency, and accuracy of the specifications. So the model actually represents what is going to be built. So the model is there that shows major functions, the information, the structure of information, information flow, the relationship among different data components, and the behavior of the system. Customer will understand what is going to be built, and this helps in the review of the software. The third important role which is being served by the model is that it becomes the foundation for the design. This model then becomes the foundation for the design, providing the designer with an essential representation of software which can be easily mapped into an implementation context. So this model is then easy for the developer or the programmer to implement it in code. The fourth important principle states, models that depict information, function, and behavior must be segregated in a manner which uncovers details in layered manner. That means partitioning. We need to partition the models. What does this mean? Problems are generally too large and complex to be understood as a whole. For this reason, we tend to divide every problem in small parts that can be easily understood and establish interfaces between these different parts so that the overall function can be accomplished. So the major problem is generally divided in small subproblems. For example, a major function is subdivided in smaller subfunctions, which are then connected together to form a complete structure. So this fourth analysis principle is suggesting that information, functional, and behavior domains of the software need to be partitioned. Partitioning actually decomposes a problem into its constituent parts. Conceptually, we establish a hierarchical representation of function or information and then partition the uppermost elements by, number one, exposing increasing detail by moving vertically in the hierarchy, or number two, functionally decomposing the problem by moving horizontally in the hierarchy. So, for example, like this is the major function, major problem. You split the problem in small parts. For example, these are the small subparts or subproblems. Subproblem A, major problem A being divided in two subproblems. Now B is again a complex problem which can be further divided in further smaller problems until and unless the problem becomes so tiny that it can be easily handled. And the interconnections among these problems are then generated. So every problem then becomes the major function of your system. Major problem was developed or coded in shape of function A, which is then divided in different sub-functions B, C, and then the function B is further split into different functions, two sub-functions. Now, when you move vertically down in tree, this will actually expose the increasing detail within this hierarchy. But if you move horizontally in this hierarchy, this will actually represent the problem by moving horizontally within the hierarchy, or functionally decomposing the problem when we move in horizontal. When you move in vertical order, the more detail about the problem is obtained, and when you move towards horizontal direction, so actually you are splitting a major problem in subparts. The last function or the last principle states analysis process must move from essential information towards implementation details. What does this mean? An essential view of software requirements represent the functions to be accomplished and information to be processed without regard to the implementation details. The implementation view of software requirements actually represent the real-world manifestation of processing functions and information structure. In some cases, a physical representation is generally developed at the first step in software design. However, most computer-based systems are specified in a manner that dictates accommodation of certain implementation details. That means software requirements engineering should focus on what the software needs to accomplish. So generally, you collect essential data from your customer, but that information actually leads you towards the implementation details. That means how the problem is to be handled when it is going to be handled by the software. So collecting essential data or collecting essential requirements from the customer actually helps you to move forward towards its implementation within the software. However, the implementation view should not necessarily be interpreted as a representation of how. Rather, an implementation model represents the current mode of operation. The implementation detail should not focus on how things will be handled. Rather, it should highlight how user would operate the software, or how the software is going to be feasible, or how the software is going to be managed or handled by the customer. So the last principle highlights the important point which we had been discussing so far, that you need to collect the essential data or essential requirements from your customer, and then collect and combine and link those information, those requirements, those data in such a manner which will help ultimately the developer to build the solution out of those. So these are the 5 basic important principles which need to be taken care while performing the requirements analysis task. That is all for now. In today's discussion, we discussed analysis principles, requirements analysis principles that help the analyst to perform his job more accurately. The first principle that we discussed was the information domain of the problem needs to be properly understood and represented. Understanding and representation are 2 aspects of the first principle. Information is something that you collect from the user, the data or the information which is actually being treated within the current atmosphere of the user. So you have to use that information, that data to implement the software solution. So information has 3 aspects that we discussed in today's lecture. The first is that the information content and the relationship between different objects of information. The second aspect is the information flow, information that is being carried forward in different functions. The third aspect is the structure of the information, how you need to give a structure or a suitable structure. Either you should store the data in tabular form, or you should store the data in tree form, the way you study in data structures. Then this is the understanding of the problem. The second aspect of this first principle is that you need to represent the information as well. Now, representation is generally done in shape of modeling. You need to design models. Now, model for a software is quite different from the models that you generally have for real world objects such as building, roads, etc. In software model, you need to draw on a paper different functions, the interaction between different functions, and the response or the behavior the system will generate in response to different functions. So this modeling will help in answering the further two important principles, which were the functions that the software is to perform needs to be defined. This was the second principle. And the third principle was the behavior of the software and needs to be represented. So you have to draw on paper the major function that your system is going to perform. This is an iterative task. You need to design again and again the model. Ultimately, you will end up with final number of functions and their interactions. And also you need to show the behavior which your software will show when some internal or external event will happen. The fourth principle states that the model that you had already drawn must represent information, function, and behavior. And that representation should be done in a hierarchical manner or needs to be partitioned easily. Now, we have defined the partitioning, or generally the partitioning is done to divide a complex problem in small sub-problems in order to make it more manageable. So the major problem or the major function is then subdivided in small sub-functions or sub-problems unless the problems become small enough to be handled by a small code. Similarly, you draw a tree of your problem, split the problem in smaller sub-problems, or the major function is split in smaller functions, and you get a vertical as well as a horizontal view of your system. The fifth principle states that the analysis process needs to move from essential information towards the implementation details. That means that you have collected all the information required for the system to be implemented from now on. All the essential data has been collected so far. The requirements that your customer needs for the software has been collected in shape of information. The structure of information has been made. The functions have been defined. The behavior of the system have been defined. These are the all important information. Now it is quite easy for the designer to have the design of the software, and this design then is easy for the developer to implement the required system. So requirement analysis actually is helping the programmer to perform the actual implementation of the software. That is all for now. We'll continue this discussion on analysis concept and principles in the next lecture as well. I thank you all.